We're going to be exploring polynomials of a higher degree. Polynomials of a higher degree, so think larger than a quadratic, potentially even larger than a cubic, are going to follow this form, which means you have your leading coefficient and your degree, and every other term after that is just 1 degree less, getting all the way down to your constant term. So some typical higher degree polynomials we use is a cubic function that's degree 3, so its largest exponent would be 3, a quartic function where its highest exponent would be 4, and on and on. After that, we don't really name them. They're just our polynomials of higher degree. Each of these polynomials is made up of monomials, single terms, separated by plus signs or minus signs if you're adding a negative number. Standard form for these polynomials is going to be written in descending exponent order. So we should have our degree or our largest exponent in the front, and then all of the other exponents in number order after that. Obviously, we know coefficients are the numbers multiplied in front of the different terms of the polynomial. Your leading term is the first term of the polynomial, the term with the highest degree. So we're talking about not just the leading coefficient there, but the leading term. Your constant term is your very one at the end, a sub 0. We're going to usually use C to designate your constant term, because C for constant. And this theorem right here is pretty important. It says that a polynomial function of degree n at most has n minus 1 local extrema and at most n zeros. So what that means is a polynomial of, let's say, just degree 2 or quadratics has at most 1 local extrema and at most 2 zeros. And that makes sense to us because if we just graph a random quadratic, we have 1 local extrema, a minimum, and up to 2 places where it's going to cross the x-axis, or 2 zeros. So we've actually used this theorem a lot in practice. You just may not have never seen it in an actual theorem. But one of the things we're going to need to talk about for these polynomial functions is the end behavior. And we've talked about end behavior before. Remember, end behavior is what direction the graph is headed in the y-axis as the x-axis approaches infinity and negative infinity. Okay, so there are 4 options for these higher order polynomials. If you have a positive leading coefficient and an even power, okay, so if you're looking at that first term, the leading term, and if that term has a positive coefficient and an even degree or an even power, then your end behavior or your graph is going to look something like this. What happens in the middle doesn't really matter. But your end behavior, what your arrows are doing at the very end, as we go to the left to negative infinity, it's going up to infinity. And as we look to the right towards positive infinity, it's also going to positive infinity. Now, if we keep that even power, but we just have a negative leading coefficient, all that means is that we have reflected this graph over the x-axis. So it's going to look something like this. That's an even power headed to negative infinity and negative infinity. So even means they both go the same direction. Positive goes up, negative goes down. That makes sense. Your odd powers, since they're odd, are going to look something like a cubic function. So a positive coefficient odd power looks like the cubic function, which means that as we go to the left, my end behavior is negative infinity. And as we go to the right, my end behavior is infinity. Okay, if we make that a negative coefficient, all that's done again is reflected this over my x-axis, so we flipped it over, which means that as we go to the left, we're going to go to positive infinity, and as we go towards the right to positive infinity, we're actually headed towards negative infinity. These 4 end behaviors are going to allow me to match up a bunch of different things for these graphs without having to do too much accurate graphing. So what we need to pay attention to with end behavior is the leading coefficient and the degree of the polynomial. Now, pretty obviously, When we're matching up polynomial functions with this graph, you could graph it, yes, but there is a way to algebraically using this information in regards to end behavior to match up this information. So let's look at these four polynomials and let's talk about their degree, which for a is 3, it's the largest exponent, and its leading coefficient, which is -7, is negative or less than 0. We know that the end behavior of an odd degree with a negative leading coefficient should have the end behavior on the left that goes up to infinity, and on the right goes to -infinity. Okay, let's do the same thing for B, C, and D before we start looking at the graphs here. The degree of B, the largest exponent is 3, and its leading coefficient is positive, so it's bigger than 0. An odd positive graph is going to have the end behavior as x approaches infinity, -infinity, that it's going to go to -infinity. And as x approaches positive infinity, ran out of room, it's going to go to positive infinity. This will help me match up these different graphs here. We keep going. C has a degree of what? 5, and a leading coefficient that is -1, so less than 0. So a degree 5, that's odd, with the leading coefficient that's negative. Odd and negative means that on the left side we'll be going to positive infinity, and on the right side we'll be going to -infinity. And for D, it's also a degree 5. It has a leading coefficient that is 1, so that's greater than 0, it's positive. So odd positive on the left side, so as we go to -infinity, is going to go to -infinity, and the limit as x approaches positive infinity should be positive infinity. Okay, so we know what the end behavior for these graphs should look like. The last thing we're going to do for these is we're going to think about that theorem that we wrote or annotated on the other page. The theorem said that any degree n should have at most n minus 1 extrema and up to n zeros. So let's look at the extrema for these different graphs here before we start matching things up. The first one has 2 extrema. So 2 extrema pieces, which means that this can be at most a degree 3. If you look at the next graph, this has 1, 2, 3 extrema showing. This counts as an extrema. It's called a tangent, a horizontal tangent. So since that has 3 extrema showing, this has to be at least degree 4. The next one has 1, 2, 3, so 3 extrema means it is at least degree 4, if not more. And the last one only has 2 extrema, which means it has to be at least degree 3. Now the reason that we looked at the degree shown on the graph is because now we can match up end behavior and degree. For this first graph, I have the end behavior on the left going to -infinity and on the right going to infinity. Well, there was only 2 graphs, B and D, that had that end behavior. One of them is a degree 3, one of them is a degree 5. This best matches up with graph number B because of the degree 3. If you notice, the other graph that has that same end behavior has at least 3 extrema, which means it has to be at least 4 or higher in its degree, which means it can't be B and it has to be D, because that's degree 5, 4 or higher. The next graph, I kind of wrote over it, but this one has on the left positive infinity and on the right negative infinity. So that's these 2 options because that's the end behavior here. And since this one has 3 extrema, which means it at least has to be degree 4, we default to making this C because that's a degree 5 polynomial, which obviously means the last one is A, but here's why. Again, positive infinity and then negative infinity. That matches up with the end behavior. And this one has to be at least degree 3, and that's what A is, degree 3. So you're matching up not only the end behavior, but also that theorem that talks about the relationship between the degree and the number extrema and the degree of the polynomial. So let's back up a little bit and let's just talk about our end behavior using these limit statements so we can get more used to them. If we look at A, 2 things we have to know. We need to know its leading coefficient and its degree. This is a degree 3 polynomial. That's its highest exponent, which means its leading coefficient is 1 x cubed, right? And that's greater than 0. For an odd positive graph, the limit as x approaches negative infinity, odd positive, should be negative infinity. And the limit as x approaches positive infinity of f of x should be infinity. Because remember, an odd positive is going to do something like that. This graph is cubic, but it doesn't matter what it does on the inside. We know the end behavior is going to be down to the left, up to the right. We'll do C so I don't have to move my screen a little bit. C is a degree what? 6 polynomial. Its leading coefficient then is 3, which is greater than 0. So we're looking at an even positive graph. Even positive, evens should go the same direction, and since it's positive, both end behaviors on the left and on the right will go up to infinity. This would look something like that, with a varying level of maxes and mins on the inside. The next one for B, I know I went out of order, we need the leading coefficient and the degree. The degree of this polynomial is 4. That's the highest exponent that it has. Its leading coefficient is 2, which again is bigger than 0, which means that the limit as x approaches negative infinity for this function f of x is also going to go to positive infinity, the same direction for even. And the limit as x approaches positive infinity on the right side will also go up to infinity. The last one here, D, is a degree 3 polynomial. That's its highest exponent. And since the leading coefficient then is negative 1, that means its leading coefficient is less than 0. So odd and negative. Odd and negative means that when we go to the left of this function, our graph should be going up to infinity. As we go to the right of this function, our graph should be going down to negative infinity. Hopefully those arrows are helpful. Another part of polynomial study is talking about the zeros of polynomials. And again, we've done this before, so if we're going to find the zeros of these polynomials algebraically, we need to factor them. If you notice in this f of x function, each of those terms has an x in it. So I can factor out the x, which is like reverse distribution, right? And then I can factor using the guess and check method. If I set up my guess and check, this is going to be an x and this is going to be an x. I am looking for factors of 6 that would that would add to make negative 1. Okay, now we're doing this all in our head, but in case you need it, here are the factors of 6. And there's a way I can combine these rows to make negative 1, and that's with a positive 2 and a negative 3. Because 2 plus negative 3 is negative 1. Now, if that's my polynomial, that means, because of the zero product property, that one of my zeros is 0, one of my zeros is negative 2, and one of my zeros is 3. in the second one, again, both of those terms have an x in them, so I can factor out that x. We'd have x squared minus 49 left over. And hopefully you recognize that that's the difference of two squares. So I can very quickly factor this to x minus 7, x plus 7, which means that my factors are x equals 0, thanks to zero product property, x equals 7, and x equals negative 7. From each part, each factor of that polynomial, you set equal to 0 and solve. Now, with these higher order polynomials, we're going to have something called a multiplicity of a 0. So if if f is a polynomial function and x minus c raised to the m power is a factor of m, then c is a 0 of multiplicity m of f. What? So we are saying that this number c that's plugged in right here would be a 0 of the function this many times, whatever the degree or the exponent on that particular factor is. A 0 of a multiplicity where m is greater than or equal to 2, so anything other than 1, is called a repeated root. So just like we did a second ago in example 3, a and b, by finding the factors, setting them equal to 0, we can do the same thing for this complicated or higher order polynomial in example 4. This part right here tells me that I'm going to have a 0 at 3, and this one tells me I'm going to have a 0 at negative 2. But I can also talk about the multiplicity. Since that factor, x minus 3, has a what is that called? Exponent of 3. Wow, I just blanked on the word exponent. It has a multiplicity of 3. And since x plus 2 has an exponent of 2, it has a multiplicity of 2. So both of them are repeated roots. Now what's cool about recognizing multiplicity is that's going to help us sketch these functions. When we sketch them, we need to know about multiplicity. If a polynomial function f has a real 0 c of odd multiplicity, so 3, 5, 7, 9, then the graph of f crosses the x-axis at that point c comma 0. The value of f will change sign, so it's going to go from being underneath the x-axis to above, or from above the x-axis to below. If a polynomial f has a real function of even multiplicity, so 2, 4, 6, 8, on and on, then the graph of f bounces off the x-axis at c comma 0, and the value of f does not change signs. That's important. Everybody highlight, circle, star, underline, does not change signs. So it's going to bounce back. So in summary, and these are things we already know, let's say I have a quadratic that has one solution. Okay? Now this is considered bouncing back. It would have just one factor that's squared. This is the value c. It bounces off of c because of the even multiplicity. But if I look at some sort of like odd graph, something like this, I have one value c here as well that it crosses. Okay, it doesn't bounce out, it actually crosses at that point. That's because this value c would be some sort of odd number like 1 or 3 or 5 or 7. Its multiplicity would be odd, so it actually crosses through the x-axis. So that information about the multiplicity and how it relates to graphing is going to help us answer these questions and sketch the graph. So let's start by stating the degree of the polynomial and list the zeros. We're going to talk about multiplicity, end behavior, whether it crosses the x-axis, and then we're going to sketch, which sounds like a lot, but hold on. So the degree, pretty easy, is the highest exponent. Well, you're probably like, well, Ms. Quigley, none of these are terms, these are the factors multiplied together. Okay, cool. One of the factors has a multiplicity of 3, the other has a multiplicity of 2, so the degree of this polynomial is 5. Since all of the first terms, x and x, in both of these factors are positive, then the leading coefficient is also going to be positive. Which means with an odd positive graph, our end behavior is going to look like this. The limit as x approaches negative infinity will be negative infinity, and the limit as x approaches positive infinity will be infinity. Okay, so we know our end behavior, we know our degree, we know our leading coefficient. We just need to talk about our zeros. Well, zero product property tells me that I'm going to have a 0 at x minus 2. I'm going to have a 0 at 1. Because if these are the factors, the zero product property lets me know that these are the zeros or solutions. Okay, we need to talk about the multiplicity here though. The first one, x minus 2, has a multiplicity of 3, and since that's odd, it's going to cross through at negative 2. 1 has a multiplicity of 2, which means it does not cross. It's going to bounce off the graph, or the x-axis right at 1. The very last thing we're going to do here, just to make sure our sketch is pretty accurate, is we're going to find our y-intercept. But the y-intercept is real easy to find. Remember, our y-intercept is found when the x is 0, so we're just going to plug in 0 to this function. 0 plus 2 is 2, 2 cubed is 8. 0 minus 1 is minus 1, and minus 1 cubed is 1. So our y-intercept is 8. That totally gives me enough information to sketch this graph. Remember, sketch, not accurately graph, but sketch. Let's start by sketching our x-intercepts, our solutions. We have an x-intercept at negative 2, and we have an x-intercept at 1. We have a y-intercept at 8. We'll call that 8. This is going by 2's. We know our end behavior, and we know when and where it should cross and not cross that x-axis. Our end behavior is negative infinity on the left side. So let's start graphing. We're going to get to negative 2. Can I cross through, or do I have to bounce back? Yeah, I'm going to be able to cross through here. I make it all the way up to that y-intercept, and then I'm going to start curving back down because I need to eventually get to this 1. Now at 1, because of multiplicity 2, I'm not actually going to cross this x-axis. I'm going to let it bounce right back off and finish with my end behavior. That's a good enough sketch of this graph using all of the information. We've talked about its degree, odd, its leading coefficient, so its end behavior, which matches. We've talked about the places where it's going to cross or touch the x-axis and bounce off. And we found our y-intercept. Those are the pieces you need to sketch the graph of these higher order polynomials. If we were to actually put this function f of x into like Desmos or a calculator, it probably wouldn't look exactly like this. There might be some crazy things happening in here, but we know at least at these points, this is right, this is right, this is right, and here, and here. Okay, let's do b together. The degree of b is 5 because it has multiplicity combined of 5. This one's leading coefficient again is going to be greater than 0 because there's no negative number I'm multiplying in the front, which means we're going to have end behavior as x approaches negative infinity going down, and as x approaches positive infinity, positive infinity. So something like that. Okay, let's talk about the zeros. This should have a 0 at 1 and a 0 at negative 2. The multiplicity of the first one is 3. Since that's odd, that means it's going to cross through the graph at 1. And the multiplicity of negative 2 is 2, which means it does not cross. It's going to bounce back. Last thing we need to do is find our y-intercept, which means we're going to evaluate the function at 0. 0 minus 1 to the third power, and 0 plus 2 to the second power. 0 minus 1 to the third power is minus 1. And 0 plus 2 to the second power, that's 4. So my y-intercept is negative 4. That's enough information to sketch. We start with our x-intercepts, negative 2 and 1. And we have our y-intercept. And we know our end behavior. We can sketch. We know our end behavior is down to negative infinity, so we're going to start there. We're going to make it to our first x-intercept, and we know that because of multiplicity 2, this does not cross. We're going to get to our y-intercept, go through it. We're going to get to our next x-intercept, and this one, because of its odd multiplicity, is going to cross through, and then I can finish my function, following the end behavior determined at the beginning. The last piece of today's lesson is about the intermediate value theorem. This theorem states that if the function f is a continuous function on the closed interval between a and b, and f of a is not the same as f of b, and k, the value k, is any number between f of a and f of b, then there is at least one number c in the interval a to b, the closed interval, such that f of c is equal to k. I'm sure you're like, Miss Quigley, what in the world? That doesn't make any sense. It really does. Picture this. Let's say we get up in the morning. We'll get up at a reasonable time. We'll get up and go outside at 8 o'clock, as if you're headed to school. And since it's decently warm outside, we're going to say when we woke up at 8 o'clock and walked outside, it was 78 degrees. Okay, let's say you go outside to change classes around 12:15, like you're headed to third period. And you walk outside and it is blazing hot. So let's say it's 92 degrees outside. If you know that this information is true, that you have an input time and an output temperature, at some point today, was it 88 degrees Fahrenheit? I mean, obviously, yes. To get from 78 degrees to 92 degrees, we have to go through 88 degrees. At some point today, was it 90 degrees Fahrenheit? Yeah, obviously, yes. At some point today, at some time, it was 90 degrees, if it made it to 92. Has it been 98 degrees today? Yeah, we're not sure. This theorem doesn't really tell us, but we know for sure that the other two, the values in between the lowest and highest value, obviously have to be reached for this function. So here's what this looks like graphically. Okay, makes sense in real world. We have a graph of between a and b, that's my interval. And if we evaluate f of a, we get some value, some output f of a. And we'd get some value f of b, right, when we evaluate at b. We know that this function exists. We were told it was a continuous function, so it has to be continuous from one point to another. I can't pick up my pencil or anything. Okay, so the intermediate value theorem states that there's some number k between f of a and f of b. Then there is at least some point on that interval where there's a value c that if I evaluated at c, I'd end up getting k. There's some time throughout the day that it had to be 88 and 90 degrees since it went from 78 to 92. You can't just skip a degree. At some point in that interval, in that time slot, there was a time or a c value when it did become those temperatures. That's the intermediate value theorem. Okay, so let's talk about what this means in mathematics. Okay, so in example 8, it says show that, so we're going to provide a small, not official proof, but just some justification for if f of x has at least one solution on the closed interval, or the inclusive interval from negative 2 to 2 for the function f of x equal x cubed minus x. Ooh, okay. So here's some things we need to know. Number 1, we know that f of x is continuous. How do we know this? Because if you look at the function we're given, This is x cubed minus x. That's a continuous function. X cubed minus x is going to look something like this. It's got a positive leading coefficient and an odd degree, so it's going to have ending values like that. These create continuous functions. It's a cubic of some sort. It's continuous, and it will be continuous on that interval -2 to 2. Okay, well, here's some more information we know. We know that at the beginning of that interval, -2, that we can evaluate our function -2 times -2 times -2. So plugging in -2 cubed minus x is going to give me -6. We also know that if we plug in the final stop on that interval, 2 cubed minus 2 is +6. Because the numbers -6 and 6, between them is the value 0. So I'm saying between f of -2 and f of 2, there has to be the value 0. We know that f of x has to equal 0 for at least one solution. So here's how we justify this answer. We use the mathematical symbol for the word therefore, 3 little dots, and we write the sentence, there exists a value c between -2 and 2, so that interval, such that f of c has to equal 0, which is what we're asking to justify. And make sure you tell me that that is due to that intermediate value theorem. So we're writing justifications, which really is going to help us whenever we get to calculus level questions, because we have to write our answers in like complete sentences providing justifications. So there exists a value c. We found that value c between the two values such that f of c equals to 0 because c is between -2 and 2. That's the intermediate value theorem. Here's what it looks like kind of in a real-world situation. A car travels on a straight track during the time interval from 0 to 60 inclusive. The car's velocity v, measured in feet per second, is a continuous function. That is super important to know. Let's highlight that. We needed that information. The table below shows the selected values of the velocity. For 0 less than t less than 60, so that's the values in the table from 0 to 60, must there be a time on t when v of t is equal to -5? That's the question. And we need to justify our answers, okay? This vocabulary right here that says must there be a time, that's very calculus. So have your spider senses go off on that we should be looking at that intermediate value theorem because we're looking for a specific time on our table or in our intervals. So what we're looking for is an output of -5. Would an output of -5 be here in between these two values? No. Here? No. Not there. Not there, but to get from -10 to 0, I would have to pass through -5, and this is a continuous function. So this interval right here is going to become very important for me in my justification of this answer. Because getting from -10 to 0, you have to pass through -5. We can justify our answers. So we're going to say, number 1, we know that v of t is a continuous function. They told us this. It's continuous between our interested interval between 35 and 50. That's where we're really interested. Because plugging in 35 to this function gets me an output of -10, and plugging in 50 to this function gives me an output of 0. That's straight out the table. We know that somewhere in between these two values is -5. Right? In between those two values of -10 and 0, there has to be a -5. So we write our sentence. Therefore, 3 little dots. There exists a c value between 35 and 50 such that f of c is going to equal that -5 value that we want due to the intermediate value theorem, which you can shorten to IVT. This is wild and cool stuff, but it allows us to use these higher order polynomials and determine if functions exist for them, which will be very helpful for us in the next lesson when we start trying to write the real zeros of these polynomials. Thanks for hanging in there.